The Irrationals. Square roots of non-perfect squares. That is, square roots of n, where n is an integer which is not a perfect square. The first set of irrational numbers we will look at are the irrationals produced by taking the square root of a non-perfect square. P is a perfect square integer if the square root of p is equal to the square root of v squared over 1. A perfect square is a number which produces a whole number when its square root is taken. A whole number is a rational number, which means a fraction. Whole numbers have denominators of 1. A non-perfect square is a number which is not a perfect square. N is a non-perfect square integer if n does not equal v squared over 1. Some examples. 4, 9, 16, 25 are perfect squares, as their square roots are 2, 3, 4, and 5, respectively. 2, 3, and 5 are not perfect squares, as their square roots are 1.414, 1.732, 2.236, respectively. The square root of a number x is a number y, such that y squared, which is y times y, is equal to x. Multiplication comes with the idea of adding by groups. Each member of the group can be lined up in one dimension, and then you count down a different dimension, such that y times y would have equal lengths in one dimension versus another, which if these objects were boxes would give us a larger box. Y squared can be visualized by drawing an actual square, where y times y is the length times the height. X then represents the area of the square. The root of the square x is y. Let's sidetrack for a moment to talk about dimensions, and we will do so by starting from some basics from reality. First point. Objects exist, have mass, and take up space. Second, the amount of space an object takes up can be visually compared to the amount of space a different object takes up. However, in order to compare the amount of space they take up, rules need to be established and followed. For example, from this point of view, which object takes up more space? The chair or the apple? The moon or the house? If we make a rule like the objects must be touching to compare the amount of space they take up, suddenly we don't have to think apples can be bigger than chairs, so long as we change our point of view. Now we know that apples are always smaller than chairs. To make that untrue would be to make a visual illusion of perspective. Perspective being the idea that the appearance of objects to an eye changes in respect to their relative distance and position. All that being said, we could simplify that into a rule like, the measurement of objects is best approximated by lining objects up, i.e., putting objects on one line and checking how much of the line they span. Therefore, we need 3 different lines: north to south, east to west, and up and down. We could add more lines, like northeast to southwest, but since northeast is made up of north and east, and southwest is south and west, we could describe the span of the northeast to southwest line with the first 3. To maximize that rule, we could standardize the measure by dividing the ruler into equal units. This way, we don't have to say that the north to south side of a chair is the same as 7 north to south side of an apple, which is the same as 6 east to west side of the same apple, as 1 east to west side of the apple is the same as 0.0857 of the same apple. We could use instead the span of something that is roughly the same for most people. Say the span of length between your fingertip to that first groove where your tip hinges. It's about 1 inch. The span to that second joint is about 2 inches. Using the standardized method, we could say that the apple is 3.5 inches in the east to west direction and 3 inches in the north to south direction. Let's bring this back to square roots. The root of a square is the span of length of one of the sides of the square. And we know that if it is a square, then it has 4 sides, and those 4 sides are equal. So the root of a number means that we are assuming the value we have is the area of a square, and that it has 4 sides which are equal, 2 of which are multiplied together to get that area. So the root value of a square can be found in the length of just one of its sides. The square root provides a great approximation to the measured value, that value being the 2 equal products of every number. As such, we can know that 1.1421356 times 1.41421356 is going to be basically 2. If every square root gave a rational or whole number value, then that would mean that prime numbers not only don't exist, but also that every number ever would also be a product of 2 smaller numbers which are equal in value. This would mean that numbers like 2 and 3 are numbers which are the result of yet smaller numbers of equal values, or it means that numbers like 2 and 3 do not exist. So then 1 and 2 and 3, etc. lose their meaning as numbers. Since not all numbers can be the product of smaller values, not all square roots can be rational or whole. Some square roots must be irrational. The number 2 is the base case of this example. 2 is the idea that one object is similar to another object in some measure, such that there are 1 plus 1 equals 2 members in the group, sharing that similarity. It is with the value 2 that multiplication becomes a thing. So to assume that 2 is also a multiple of something would make no sense. It is the idea that a column of 2 things, doubled, results in 2 rows and 2 columns each. Multiplication adds rows. Before 2, there was just individual entities, and you could line them up, but you were too concrete of a thinker at this stage to see any similarity between them. So you would just have a line, a row, with one object per span of line. Multiplication is useless here. At this point, the one lining up the individual entities might induce that they are now similar in that they all share the fact that they have been lined up. But multiplication does little here. Since there is no point in multiplying before the advent of the number 2, it obviously follows that we did not get the idea for a number 2 because we needed a value that was the result of some multiplication. We know that the number 2 comes from the idea that we have 2 hands, 2 feet, 2 legs, 2 arms, as opposed to 1 head, 1 tongue, 10 digits on the hands, etc. Multiplication is used to simplify the counting we do with these values. Some values that exist and existed before multiplication was invented do not have values that multiply to result to them. We call these prime numbers. Numbers which do have smaller numbers that multiply into them don't necessarily have 2 factors which are equal. Like 6 is 2 times 3, but the square root of 6 is not a whole number. It is for this reason that square roots of any non-perfect numbers will result in an irrational number. To prove this is true, let's start by assuming that the square root of some integer n is a rational number, meaning that it takes the form the square root of n equals p over q, where p and q are integers. First, we want to make sure that the values of p and q are in their lowest form. We can write them in their factorial form, such that we have P made up of its prime factors, A1, A2, A3, etc. to AM. And Q is in its prime factor form, B1 times B2 times B3, and so on till Bk. If we are in reduced form, then there will be no value on the top and bottom to cancel. For example, if P is 35 and Q is 10, we would have in prime factor form P equal to 5 times 7 and the Q equal to 2 times 5. The 5 on the top and the 5 on the bottom would cancel. So 35 over 10 in its reduced form would be 7 over 2. If P over Q is in reduced form, then there is no A that equals any B, as in A1 does not equal B1, nor does A1 equal B2, etc. The M and the K being indexes that stand for each element in their respective sets. Now that we are in reduced form, take the square of both sides, which gives us N equals P squared over Q squared. If we recall from the definition of a perfect square, we could recall that it looks something like this. N equals P squared over 1. Therefore, we set Q squared not equal to 1, so Q cannot be equal to 1. If it was equal to 1, we would have a perfect square, which would mean that N is a perfect square and not a perfect square. So we don't allow Q to be 1. So we have N equals P squared over Q squared, where Q and Q squared cannot equal 1. And we know that the prime factors of P and Q don't equal. So that means that P squared over Q squared does not simplify any more than this. Which means that N, being equal to P squared over Q squared, is not an integer, as P squared over Q squared is rational. Therefore, N is an integer and N is rational, which is a contradiction. So this means that our assumption is false. Since we reached a contradiction about the integer of N and its square root, we need to fix one of our assumptions. Our only assumption was that the square root of N is equal to a rational number. Therefore, the square root of N is irrational. To sum up, the square roots of non-perfect squares provides us our first set of irrational numbers. With this, I think we can see the basis of irrational numbers, where they come from in reality, and why they're not mystical. In the next video, we will go from squares to circles. Don't forget to subscribe to the channel, like and share the video, and support us at patreon.com/youexist. See you next time.